Section 6.5 is where we learn to graph the other trig functions. So in 6.4 we covered sine and cosine. Other trig functions that we're going to talk about tangent. Then we're going to talk about the reciprocal trig functions, and I'm going to go cosecant, secant, and then cotangent. Once we talk about the graphs of those four trig functions, we're going to talk about some weird shifts that we can have happen to trig functions. So the way I look at graphing the tangent function is I remember that tangent is sine over cosine. And the key points that we want to graph for the tangent function are going to be our quadrantial angles. But remember that two of our quadrantial angles, tangent is undefined. And then we're also going to want to graph the multiples of the 45-degree angles, because tangent of 45 degrees is 1, and it's a really easy point for us to find. So, first thing we want to talk about is the period of the tangent function. Remember that the period of sine and cosine is 2 pi, so that I figure out how wide to graph it by doing 2 pi over the b term. So if I look at the unit circle really quick, I'm just going to put in the key points that we are going to end up using for our graph. So cosine is 1, sine is 0, square root of 2, square root of 2, 0, 1, negative square root of 2, comma 2, square root of 2, negative 1, 0, negative square root of 2, negative square root of 2, 0, negative 1, square root of 2, negative square root of 2. So those are the x and y coordinates for the information that I'm going to use to graph this. Different color, I'm going to do tangent. Remember, tangent is sine over cosine. So it's the right number over the left number. So tangent of 0 is 0. Tangent of 45 is 1. Or we're actually going to use radians, so the tangent of pi fourths is 1. 1 over 0 is undefined. This would be negative 1. 0, 1, undefined, negative 1. So what I want you guys to realize is that it goes 0, 1, undefined, negative 1, 0, 1, undefined, negative 1. If this is 0 radians and this is pi radians, we repeat our cycle every pi. So for tangent, if it is in its transformation form, which is f of x equals a tangent b times x plus our phase shift, so I'm going to make that the h, so I'm going to put x minus h plus k. That b is no longer 2 pi over b to find the period. It is now pi over b is the period of the tangent function. So that will be the same thing for the cotangent function. The period of tangent and cotangent is pi, and the period of all four of the other trig functions is 2 pi. Again, we are going to divide our period into 4 regions so that we can graph it. And for tangent and cotangent, actually most of them, they're going to ask you to graph 2 periods. So now that I know my period is pi, I'm going to divide my graph into 4 different regions. So I have pi, negative pi. This would be pi halves, pi fourths, 3 pi fourths, negative pi fourths, negative pi halves, negative 3 pi fourths. 1, negative 1. And what I'm going to do now that I have the template is I'm going to put my dots that I know, and I'm going to start at negative pi, which is rotating this way, so negative pi is 0. Negative 3/4 pi is 1. Then I go undefined. Well, where it's undefined, I have a vertical asymptote. And I know the direction that it's approaching that vertical asymptote because it's on the positive side here with no x-intercepts. So I am going to draw it going this way. So my next number I have is at pi fourths, it is negative 1. Then at 0, it's 0. Pi fourths is 1. And again, it goes undefined. So this one, that region will look like this. And you should notice your graph is going to repeat, because at 3 pi fourths you have negative 1 again, then 0. So you should notice that the graph is repeating with a period of pi. One key thing that I would like to point out is when I graph my vertical shift, I'm going to graph my vertical shift using where it crosses at 0. That helps me move it up and down. The amplitude, I'm going to use the pi fourths and negative pi fourths numbers to compensate with the amplitude. For example, if this was 2 tangent of x, I would actually, at pi fourths, it would end up being a 2. If that was 5 tangent of x, that would end up being a 5. So that's how you end up graphing the tangent function. Again, that's amplitude. Pi over b for period. That's my vertical shift. And when I factor the b out, that would be my horizontal shift. For the next 3 functions, the way I want you to remember how to graph these is to roughly sketch in their reciprocal functions. So cosine's function is reciprocal function is sine function. So what I'm going to do is I'm going to graph a couple periods of the sine function, and I'm going to graph it with a dotted line. And you should remember the way I told you to do the sine function is to remember that it starts at 0 going up. So all I'm going to do is to put dots in for my sine function, remembering it starts up, and then I'm going to dot in that graph. The next thing I'm going to do is I'm going to put dotted lines at the top and bottoms of the amplitude of the sine function. That's just to give me a rough guess point. And I'm going to just look at this. And remember that the cosecant function is 1 over this function. So everywhere that this function is 0, you are going to end up having a vertical asymptote because the cosecant will be undefined. So I'm now going to draw in my vertical asymptotes everywhere that sine is 0. Again, I don't have to draw on the y-axis. I'm just doing it for us to look at. The next thing I'm going to do is I'm going to, everywhere that sine is at its maximum or minimum, I'm going to just look at it. Well, the reciprocal is cosecant, so what is 1 over 1? Well, it is 1. So and then negative 1 over 1 is negative 1. So I get those points on here. And the next thing I want to know is I want to know where sine is 1/2 or negative 1/2. And remember, sine is the y of a 30 of our right triangles. And the 1/2 is going to come from the 30-degree angle, or pi 6, because that would be 1, 2, square root of 3. So it is 1/2. So sine is 1/2 at pi 6 and at 5 pi 6. It is negative 1/2 at 7 pi 6 and 11 pi 6. So when sine is 1/2, the reciprocal of 1/2 is 2. When sine is negative 1/2, the reciprocal of negative 1/2 is negative 2. So that's going to give me my next key points on my graph. So everywhere that sine is positive, my pi 6 from each end of the asymptotes is going to give me 2. So here and here, then I'm going to approach the asymptote. Same thing here. Everywhere that sine is positive, it's going to, my thing's going to approach it there and there. Same thing here. Where it's negative, it's going to approach negative 2 at my pi 6. And on this last one. Okay. The green graph is the graph of my cosecant function. The red graph is what I use to help me come up with my function. My recommendation is that if a cosecant function has shifts in it, is that you work with it as, turn it into a sine function, and then work with it as a sine function, and then take the reciprocal of that function to take into account any of the shifts. The work would probably be much easier. So similarly, I am going to graph the secant function by first graphing the cosine function. So pi, actually that's 2 pi, negative 2 pi, 1, 2, 1, 2. And the way I told you to remember how to graph the cosine function is cosine starts at its maximum and goes down. So if I start at my maximum, which is 1, going down first, this would be the quadrantal angles for my cosine function. And I'm going to dot that in. Just like the cosecant function, for the secant function, the next thing I'm going to do is put in my vertical asymptotes. This time I'm going to put my vertical asymptotes everywhere that cosine is 0. And I'm going to give my helper lines. All these dotted lines are not part of your graph, with the exception of the vertical asymptotes. Next thing, everywhere that cosine is 1, my secant is 1. And everywhere my cosine is negative 1, my secant is negative 1. So I am going to put in my 1s. Where I was looking at my pi 6 angles to figure out where the 1/2 was to turn it into a 2 by the reciprocal. For secant, I'm going to look at where cosine is 1/2. And that is when this angle is pi thirds. So it is, cosine is 1/2 at pi thirds, 2 pi thirds. It's negative at 2 pi thirds. At 4 pi thirds, it's negative. And at 5 pi thirds, it's positive. So it's at the pi thirds this time. Okay, notice here that my pi 6 are close to the asymptote. The pi thirds are going to be closer to the halfway point. And everywhere that I'm at one of these pi third angles, My cosine is 1/2 or negative 1/2. Therefore, the secant is going to be 2 or negative 2. So where it's positive, it's going to become a 2. Where it's negative, it's going to become a negative 2. Actually, I need to make it closer to the dot. Positive 2. Negative, negative 2. Positive 2. And then I draw my smooth curves and they approach the asymptote. Similar to these two, that's the same way I'm going to come up with a cotangent function. But once I graph the tangent function, all I really do is I flip the tangent function upside down. And that's how I'm going to end up with a cotangent function. Or, let's see. That's actually not how I'm going to end up with it. Because cotangent is equal to cosine over sine. So we're going to end up with different undefined points. I'm still going to do the quadrantals and the 45s. So going back to the numbers I put in the unit circle, I'm going to end up with undefined, 1, 0, negative 1, undefined. Undefined, 1, 0, negative 1, undefined. And repeat, 1, 0, negative 1, undefined. Period, again, is going to be just pi. So I graph it just like I graph the tangent function. Everywhere that it's undefined, I put vertical asymptotes. Everywhere that it's 0. And then at my pi-force angles, that's where my 1s and negative 1s are going to be. So it's going to look just a little bit different. So my period, break each, the positive and negative, up into 4 equal pieces. So my undefineds first are at 0, pi, and negative pi. So my asymptotes are going to be at 0, pi, and negative pi. My zeros are at pi halves, negative pi halves. And notice at pi fourths it's 1. So let me put my 1s in here. Then at negative, and at 3 pi fourths it's negative 1. So you should notice that the cotangent function, the curves are in the opposite direction of the tangent function. Okay? They're flipped upside down. And then they're shifted. How far are they shifted? They're shifted 90 degrees. So the way I graph cotangent is I graph the tangent function, negate it, and shift 90 degrees. Or you can remember it's cosine over sine. Remember that the tangent of an angle is equal to 90 minus the cotangent of an angle. Or the cotangent of an angle is equal to 90 minus the tangent of an angle. That's why that shift works. The same shift works between cosecant and secant. Just like the same shift worked between our sine and our cosine graph. They're just shifts of 90 degrees. So that's how you come up with the basic graphs for the other 4 trig functions. For cosecant and secant, you sketch in the graphs of their reciprocal functions. For tangent and cotangent, you evaluate where sine over cosine or cosine over sine to come up with those. The next part of the video, I'm going to work through some of the weird amplitude type problems. So let me erase this, then I'll get back. So I'm going to cover 5 different trig graphs, but in order to do those 5 different trig graphs, first thing I'm going to do is come up with the sketches of 3 non-trig graphs. I'd like you to notice that in front of each of these basic trig functions, sine and cosine, I've got, like here, I've got an x. Here I've got a quarter x squared, e to the x, absolute value of x. And remember that this is in the a spot of my formula for the transformation. So this is the amplitude of my function. So it's no longer do we necessarily deal with constant amplitudes. We're dealing with an input function to the amplitude of the cosine function. So, quick reminder that absolute value of x is a 45-degree angle like that. So, at 0, the absolute value of x is 0. So where cosine is normally 1, it's going to be 0. And then it's going to move its way out. So if you have a you have a multiplication problem or a composition of functions in a multiplication problem, first thing you want to do is you want to sketch the part of the multiplication problem on your graph. And if it's outside by itself as a multiplication problem, what you're going to do is you're going to graph it as well as graph it flipped over the x-axis with dotted lines. So what I'm going to do is I'm going to dot in my y equals x, my absolute value of x, top and bottom. And then what I'm going to do is, I'm now going to graph either the sine or the cosine function, and instead of bouncing between 1 and -1, I am going to bounce between these points on my dotted line. So cosine cosine starts up and goes down. So it's going to start at the top, going down, and then up, and then down, and then up. And then here it would go up like this. So basically you are using the function that you're multiplying by as the bounds of your amplitude. Now when it comes to this last problem we are going to do, we are going to end up actually taking a similar graph where this is cosine. When we do that one, it would be the x sine x graph, but everywhere that it's negative here, it would turn into a positive little hump line there. For the next graph, e to the x. This graph, e to the x sine of x, or e to the x cosine of x, actually, I'm going to do e to the negative x, which is 1 over e to the x. So that way we get this graph. This graph right here, with using this restriction on a sine or a cosine function, actually models like if you take a door that has a spring on it. As it swings, it's going to go closer and closer and closer and closer until it finally stops. That's what this is going to end up mimicking. But again, we're going to graph the e to the negative x function. And e to the negative 0 is 1. Is 1. So we're going to dot those graphs in. And then we're going to graph our sine function. And remember, the sine function starts at 0 going up. And it's going to have the same period as your normal sine function. And basically the sine waves are going to get closer and closer to 0. Mathematically, they would never get to 0. In real world applications, yes, they will get to 0. So basically what I'm doing is I'm using this number that we're multiplying by, this function that we're multiplying by, to give me some bounds on my function. 1/4 x squared is a parabola that shoots up slower, so it's going to be a very wide parabola. So the graph of 1/4 x squared, I'm going to do it like this. So I'm going to dot that graph in. So at 4, I'm at 1. And make sure to dot it upside down also. Sine starts at 0 going up. So again, I end up with a curve that looks similar to this one. It just has different scaling factor here. Next one's going to be x cosine x. The thing that's different about this one and the absolute value function, with the absolute value function in front of it, it's always going to have that 1 for the amplitude. Well, here, my x cosine x, my x graph is this diagonal line. So this is my primary. I got to remember that when I am negative, I have to flip my cosine graph upside down. So where cosine starts at 1 going down, on the other side, it's going to start at, when I go negative, I'm going to start at 1 going up. But it does a whole bunch of quick oscillations here. So I start at 1 going down here. Well, 1 times 0 is 0, but I'm still going to go down. Normally, I would start at 1 going down, but because this is negative, I am going to go up first. And I'm going to emphasize that this is a down first. So that's how I would get that graph. Sine graph, x sine x, and then take the absolute value of that. So first thing I'm going to do is I'm going to dot in my x using the same thing I did here with cosine. Now I'm going to dot in the sine function, and then everywhere that it's negative, I'm going to turn it positive. So sine starts at 0 going up. So it would go up, and then down, and then up, and then down. Starts at 0 going up, but that's a negative. So instead of 0 going up, it will go 0 going down. Okay. Now what I'm going to do is I'm in red. Everywhere that this graph is negative, I'm going to turn it positive, and then I'm going to, on the positive portions, I'm going to keep the same. The only homework problems I assigned that were like this, you are actually matching graphs to functions. So my recommendation is that you put these 4 graphs into your notes, and maybe the steps on how you come up with these into your notes. And if worst comes to worst, get your graphing calculator out. Make sure you're in radians mode. Type in the function. If you need to do an absolute value on the graphing calculator, there is a math section, and the absolute value, there's a function called ABS. Your other option is go ahead and use Desmos to graph them. But I want you to understand how these graphs get their shapes. So that would be it for section 6.5.